Okay, this is your classic plotting question, and as you know, I prefer to take a different approach to these questions. I want you to actually know something about polynomials and other functions, and be able to graph it somewhat intuitively when possible, and then use the calculus to verify what your intuition told you. But you could just use calculus to do the whole thing, and there are some times when you have to rely on the calculus. But you have to kind of think about this and say, is this one of those problems where I can use some quick plot tools? And in this case, yes, you can, because we have a x to the cube that we can factor out. And furthermore, you do this and then you say, oh, wait a minute, now this factors even further. X plus 2, x minus 2. So we have only real roots, and so we can sketch over here. We can say this should look, well, I don't know why I'm not getting straight lines here. There we go. Okay, so I have a triple root at the origin, and I have a root at plus and minus 2. And what do I have? As x goes infinite, then f goes infinite, so I'm coming in from the first quadrant, and then I'm going to turn around and come in like a third order, like an x cubed function. Then I'm going to cut through this way. And it should be symmetric. I haven't drawn it perfectly symmetrically, but this is the function we're looking at. Knowing that will help us interpret everything else that happens. So now we go about the question as specifically asked. It says use the second derivative and the first derivative. So let's go ahead and calculate those. F prime is going to be 5x to the fourth minus 12x squared. And again, you can factor x squared out of this. Now, when you see 5x squared minus 12, you should say, oh, that factors again. But it doesn't really matter where it factors. You just know that it's going to be, x squared is equal to, excuse me, 12 over 5. And so x is going to be plus and minus that. But what you should just see, you should see this structure as a perfect square right here, including x. And that doesn't matter that there's a constant in front and that they are minus 12. You just see x squared minus, and you just automatically know those two roots are going to be symmetric on either side of the origin. Okay, so let's deal with that later. Let's think about what's going on over here. Take the next derivative. Okay. Again, you can factor out something. Oh gosh, you can factor out a 2 or a 4. Let's factor out a 4x. Okay, I'm going to get rid of a 4, so I'm going to have 6 left in here. Okay. And so what am I going to do? It says, so I used the first derivative. I haven't used it, but I calculated it. We need to find all critical points. Aha! So this is, by looking at my plot, my critical points should end up here, here, and here. And my points of inflection should end up here, and here, and here. So we should get 0 coming out both times, and we will, see. Now let's go work on this. Okay, so x equals 0 is a critical point. And then 5x squared minus 12 equals 0 is 5x squared is equal to 12. X squared is 12 over 5. X is equal to plus or minus square root of 12 over 5. Okay. And if you calculate that, that's approximately plus or minus 1.55, let's just say. So those are going to be critical points. And it says use the second derivative, it says, classify each. So we'll classify later. Let's just find all these guys first. X equals 0 is, it's going to be a point of inflection, but we're not entirely sure. These are possible points of inflection. Because of the stacked roots, we know from looking at the picture that this is going to be a point of inflection, but we don't know from the calculus yet. So then we have 5x squared minus 6 is equal to 0. 5x squared is 6. X squared is 6 over 5. X is equal to plus or minus square root of 6 over 5. And that's going to be approximately plus or minus 1.095. Again, just stick that into your calculator. And we're going to ask if these are points of inflection. Okay, so right now we're doing pretty well. We just have to completely finish this. We've got everything going. We have to justify with the calculus why our plot is. Oh, it said both coordinates. Whoops. Okay, I guess we need to find all the coordinates. So x and y, and then type. I'll go ahead and put them in a grid like this. Okay, so x could be negative square root of 12 over 5, negative square root of 6 over 5. It could be 0 square root of 6 over 5, and whoops, bring those bars all the way over, and square root of 12 over 5. Do the easy one. Okay, so let's see, we have to do some plugging into your calculator. So actually, which one of these is easiest? Like, we could use this format, or we could use this format, or this format. Doesn't matter. I think the way it's given originally in the problem is actually the easiest way to key it into your calculator. So let's go ahead. I'm just going to tell you what I would key in. I would say, again, for minus square root of 12 over 5, if we've already figured it out that that's 1.55, then I would say 1.55 to the 5th minus 4 times 1.55 cubed. And that's going to give us 13.3 down here. Actually, it's going to give us negative 13.3. Let's see, line this up. So, okay, this guy is going to be negative 13.3. Do the same thing with a negative sign in there, and you're going to get positive 13.3. Okay, and then you do the same thing for 1.095, and you're going to get 3.68 and negative 3.68. And then just by looking at the plot here, you're going to be having a max, point of inflection, point of inflection, point of inflection, min. So now we have to use calculus to justify this. It's the classify. So it's the show all work bit. That's the last piece that's missing, is the show all work. Okay, so we want to demonstrate why this is a max, for example. Okay, so we can say, I just wish I had a little bit more space. I'm going to try to squeeze over here. You should not do the same. I'm just constrained by this screen right now. Okay, so this guy is a max because, and there's a lot of things you can say. So for example, you can show me that at, for example, this value negative 2, you can show me that there's a 0, and then later there's a 0, and that it's got to be a max, because if there's a single point where the derivative is 0, and we know that the function is strictly positive and it's 0 on either end, then that has to be a max. And you can write me a paragraph that says that. But the easiest way is to actually look at the second derivative, because y double prime at this point, hold on, you look at the concavity. See, if it's concave down, then you have to have a max. So let's just calculate this. So is 20 times minus square root of 12 over 5 cubed minus 24 minus square root of 12. Oh, I'm having trouble with my technology here. Minus 24 square root of 12 over 5 this is a piece. I'm having trouble putting it there. There we go. If you type that into your calculator, this should be negative. Now you need to write that out. I don't want to, oh maybe I'll just go ahead and calculate this. Alright, so let's, so your negative square root of 12 over 5, we said negative square root of 12 over 5 is about this value, negative 1.55. So let's calculate this. 20 times negative 1.55 to the power of 3 minus 24 times negative 1.55, and then I double check to make sure I've typed it in correctly. 20 times, and yes, this is the value I wanted, negative 1.55 cubed minus 24, yes, equals negative 37.27. So concave down, it's a max. Okay, and you use a very similar argument for the other guy, and you would say, so square root of 12 over 5, negative 13.3 is a min because, and then 37.27 is positive. Y double prime positive means concave up. Okay, so we've now justified the max and the min. We now have to justify the points of inflection. And let's see. So the deal with the point of inflection is if you have a change in concavity. In other words, you show you're going from positive concavity to negative concavity, you're good to go. So the only problem we have is if we have stacked up roots such that, for example, like, you know, y is equal to x to the 5th actually has a point of inflection right here, but you can't just use two derivatives to show it. That's a little more complicated. But right here, we've bottomed out. We're done with stacked derivatives. We've actually gotten ourselves out of them. And so all the points of inflection, all three possible points of inflection are points of inflection because roots are order 1. In other words, they're like a line. And sine of f double prime changes when we pass through them. Okay, so I mean, you could use, this is like an essay style response. When I say show all your work, you can use an essay style response, or you can use formulas and equations. Either one is showing all work. But for the maxes and mins, I was choosing to use more of a formula-based approach with a little bit of discussion thrown in. And now for justifying the points of inflection, I'm using more of an essay type explanation. So the point is, if the sign changes, you know you're switching from spilling to holding. And when you switch from spilling to holding, that's a point of inflection. So maybe I should write that for you to remind you. If you switch from, now I'm going to abbreviate, spilling to holding, this is a point of inflection. Okay? So that, anytime that happens, you've justified the point of inflection. There's more to be said on this topic, and it very well will come up in another question. If not, let me know, and I will post more videos with more questions.